All right, you ready to go? So we're talking about piping systems. I wanted to make sure that, did I adequately cover the solution to Chapter 1, Problem 9? I thought I did. Did I? Okay, we can visit that if you like. And I'd like to talk about 22, which was due today. Very challenging problem. And if time permits, talk about 27, which is due next time. First things first, I'd like to, did I show you, if you just do a Google search on Excel and ME, EXCEL and ME, you can come up to a University of Alabama site. I show this to students in thermo, and there's thermodynamic software, heat transfer software, thermal systems software. So click on that one, and in the energy or thermal systems design class, they talk about the Churchill friction factor, the Hardy cross, and maybe a few other things. Did we download that, or did I show you or encourage you to download it? So the add-in as well as the help, make sure and grab the help for that. And one of the things, let me jump over to Excel. Let me see if this is running here. What do I? So in Excel, go to like the file, then options, and the add-ins, and then just make sure that you have that add-in added in. Okay. Let me do cancel on that. So if I say the friction with the Churchill, I think I've shown that to you. That's where that comes from. There's another equation, Swami. But you can also do Hardy. It's the Hardy cross with the Hazen-Williams, or the Hardy cross with the Darcy-Wiesbach. And so let's do this one right here, hit tab, and then go to the help. And what I thought was neat was that not only are there a lot of inputs, but there's help on this function. And they have the Hardy, Hazen, and then describe. And where did that table 1-5 come out of? Straight out of our textbook. Couple? No. And then table 1-6 straight out of the textbook. They have an example. And I think this is the example straight out of our textbook as well. And they talk about the connection matrix, so they transpose it and talk about flows. And oh, by the way, they even have a neat little shift control enter instead of hitting OK when you want to execute that, because you're feeding it matrices and it's doing matrix calculations. And they cite the textbook that we're using. So anyway, I thought I'd point that out. How many people have laptops? They may want to load that up. You probably, some of you worked with developer. You have to turn that in the toolbar on. Otherwise, it doesn't normally is on, but if I hit developer, then I could go to the Visual Basic. There's a lot of stuff that I have that I play with or go around in. And let me try and clean up some of it. Get rid of this, get rid of the heat transfer. This is the one we just added on. And let's see, these worksheet forms. This can be a little annoying. They always want you to thank the NSF for the funding the students who did the work of making the software. And it's been a while since I did it. Maybe it's here. Yeah. Put a little comment right there. That little tick mark is a comment, like that. And now you comment out, and it doesn't show you the welcome sign. And then just do a save. Up here, save as. Let's get back out of Excel, or at least out of here. To get out of this usually the way I do it, get back to the Excel file itself. Okay, so this problem was the problem that you say people have done it. We've done it. We solved this problem. True? Okay, so with the time, I won't spend more time on this problem. Let's move to this problem. So a piping system connects a chiller. Here's the chiller down here. and that chiller supplies cold water to air handling units. They introduce floors of a building, although the elevation isn't important, it's really the distance. Elevation's important when you have an open system or you actually want to know the actual pressure, because obviously hydrostatic is going to be lower at the higher floor. It'll be lower pressure at the higher floor. And in the basement, you'll have the higher pressure. But we can ignore the elevation and just think of the floors as distances they have to travel to get there. It needs to provide the flow rates as shown. So 3, 3, 3, 5, and 3. So 17 is what needs to come through that main loop. And there's only 3 pipe diameters, main loop with and risers. So all of these have the same diameter. And then the floors with the single air handling unit and the floor with the 2 air handling units. Those are the 3 distinct. Size the pipe so the velocities are less than 10 foot per second. This was 120 what, 2? Or 20, 22? All right, so this is the problem 22. All right, so we have the fluid properties. We have the steel pipe with the roughness. And I highlighted 3 diameters, and those I'm going to input. And these I could have started with 18 inch and 10 inch and 12 inch, and so whatever it is. So I have how many legs did I define in the system? 14 legs. There was a little difficulty, and some students stopped by and wanted to talk about how you define the legs. Well, the legs have to have the same flow. You can't split it and still follow one part and call that a leg. And so this is leg 1. It starts from this node way up here and goes all the way to this node. But then 2 is a very short leg, and 3 is a short leg. I went ahead and introduced 4, even though I could tell that 3 and 4 have the same flow rate, but I have a pattern. And then 5 and 6 and 7 and 8, 9, 10, 11, 12. So the flow, actually the flow in 3 is going to be the same as the flow in 4. Likewise, you could tell the flow in 11 is going to be the same as the flow in 14. But I didn't try to minimize the number of legs. I just made it understandable. So that's what I did in Excel. So we had the inputs of the length of each leg, and then this is just grabbing the information up here. So if it's a riser or the long run, all of them get the same 18 inches. If it's on a floor with the one air handling, if it's on the 4th floor with 2 air handling units, then it's 12 inches. So that 12 gets copied down to here. And so I know that we can look for more precise inner diameter of the pipes, but otherwise just use the diameter, reported diameter is the inner diameter of the pipe. So there it is in feet. There's the area, foot squared. And this is the volumetric flow rate that was input. Hence, you can get the mass flow rate. And the more critical is the velocity. So just looking at this velocity, you want to see let me do this, which one are below 10 foot per second. Maybe you say, is any above 10 foot per second? No, it doesn't look like it, does it? So, I mean, let's say if I went 16 inch, well, then it exceeds it in leg 1. So I bet I'm stuck with the 18 inch. How about, could I go with a 8 inch on the floors? Sure could. Could I go with the 6 inch? Nope. Stay with 8. And then with the the last floor, which I color-coded green, I could probably go with the 10 inch. Yeah, let's go with the 10 inch. So 18, 8, and 10? Yes?
How do your flow rates change for the vertical risers? Like how are they
Yeah, what I did was I went back here, and basically if I know that I need 3 CF cubic feet per second to go here, then I just do the math on this node. I did it. And then if I take off 3, then I do the less. And then if I take off 3, then I take off 5. That only leaves 3 left of the 17. And then do the math back here. So I figured out all the flows a priori outside of Excel. Just coded them in. Let's go back to the Excel code. So there's the diameters. That's the first part. I guess we should go back and read the rest of the problem. Now consider two options. One pump and partially closing the valves that are in the lines that have only one air handling unit. So this line up here is going to be the hard one to get 5 CF cubic feet per second because of the high resistance and high flow rate. So partially close these control valves on the first, second, third, and fifth floor. Well, how do you close them all the same amount? Nope. You sure don't. So you have to find how much you close for 4 valves. For this valve, that valve, that valve, and that valve. That's not an easy task. But that's design option 1. You only have one main pump, and you use the 4 control valves to toggle it down. And you try to get it to be the minimum head that the pump puts in, so it's minimum flow. Well, what would that be? Leave this valve as open as you can on the floor that's hard to deliver as much. You don't want to add any resistance to that floor. You want to keep the valve open. So that's the first one. The second option is to put a second pump right here, leave this valve open again, and then try to leave these other valves as open as possible, but you may have to tweak them just a little to get it to be perfectly matched so you get 3 CFM, 3 CFM, etc. But to have a second pump in that line with 2 air handling units. Let's go to the Excel code. This is where it gets ugly, right? So we identified loops and we put in a connection matrix. I think you're pretty well familiar with that. How are we going to use that? For the Kirchhoff's head law. Head drops through the loop. So maybe I should do this one. Maybe I should get rid of this. And what were the loops that I had? The first loop, go with line 1, with line 3, with line 4, 7, 10, 13, and there, that's loop 1. Loop 2 is with 2, with 6, opposite 4, and opposite 3. With 5, with 9, opposite 7, opposite 6. With 8, with 12, opposite 10, opposite 9. With 11, with 14, opposite 13, opposite 12. So that gives us 1, 2, 3, 4, and 5 loops. So we have the 5 loops, 1, 2, 3, 4, 5, and how they participate. Okay. Have the Reynolds number so I can get the friction factor using the Churchill equation. All right. All right, so then you have the energy. Because this is so tricky, I always put it in 2 units, but we're going to work in energy head, this one, foot-pound force per pound mass. This is the velocity head, energy per unit weight. If you notice that these have the same units, that's the reason I highlighted that. They have, it's different units, same magnitude. Different units, same magnitude for 2 heads. The elevation head and the energy head. Anyway, let's do this. Continue on. So we get the energy head loss. You can also express it as PSI. Then we have all of these heads for the chiller, right? The chiller is only in the first leg. The air handler unit is only in the third, fourth, fifth, sixth, ninth, whatever. And then you have the air handler unit in this leg that had 2 of them. It's quite a bit larger. So you see that the head loss is much larger. We have valves, and I want to calculate the head loss, but I have 1, 2, 3, 4 valves that I want to control. 1 valve I want to leave fully open. The minimum value for the K on the valve fully open is 0.0375 given in the problem statement. So this value, this value, this value, and that value, I can change to tweak the system to get it to be balanced. Okay? So maybe I should color code this one separate so it's not something that gets changed. That one remains the same. But you calculate the head loss across the valves. When they're open, there's very little head loss, isn't there? Okay, here's the pump head gain. I put it right up here because pump 1 and pump 2, right here, I've most recently analyzed the system with both pumps running. Okay, so if I have both pumps running, then the pump in leg 1 and the pump in that leg with 2 air handlers is increasing the head. So it's a head gain across the pump. So let's continue on. Here we have you could look at a PSI as well, but the total head, which is the sum of the losses minus the gain for that leg, we need those. And then what we have are the loops. How many loops do we have? And then we have a head balance for each of those loops. So how does Kirchhoff's head law apply for each of those loops? And what I want to do is I want to drive each one of those to 0. You could see how we calculated it. We used that matrix, but we multiplied by that connection matrix. It's back here. This connection matrix for which legs participate with loops, aligned with the loop or not aligned with the loop, opposite the loop, right? All right, so let's go back. So what I want to do is drive each one of these to 0. How do I do it? Well, I do the sum of the squares. Just take that vector dot product with itself. That's the sum of the squares. And now that's an objective function I want to minimize. So Excel will do its best to minimize that objective function. So let's say that I didn't know what the head was, nor the valve settings. I could start these at 0.03, 0.03. Well, that's actually too low. It's got to be 0.0375 or greater, so 0.04. Oops, 0.04. Let's come back down here. Leave that one alone. This one, fine. Leave it. I'll just leave those two partially closed a little bit. And we didn't know what the pump needed to be. It needed to be 40 and 45. And you could tell that the head balances aren't as balanced as I'd like them to be. So what I like to do is I'd come in here, that'd be my objective function, go under the data tab, go under solver, and you can see I've done this before. And let me go ahead and hit this one right here. So I'm selecting that cell as my objective function. I want to minimize it. And if you double click this helps to line it up. I'm going to change pump 1. I'm going to change the K value in these valves. And what I need to do though right here, this one right here, I need to also change that second pump. So it's 1, 2, 3, 4, 5, 6 things that are going to be changing to try and drive that sum of squares to 0. I'm going to just scoot right here. I'll hit solve. It has to be close to the initial guess because it's a nonlinear system. We could implement a Hardy-Cross type of safer approach to it, but I didn't. I just did this. And you hit OK, and there you go. It pretty well drove it to 0, didn't it? Each one of those loops have the head balance. And it looks like we have a partially closed valve, This one's open, and that one's partially closed, but they're not closed much, are they? Pump 1 is adding that many foot-pound force per pound mass. Pump 2 is adding that much. I convert those because of the flows. I can convert them to foot-pound force per second. I can convert them to horsepower. So the first pump is consuming 68.7 horsepower and then 20 horsepower, sum of about 89.4 horsepower. I can go in here and I can boost it by, I don't know, 10,000. Boost it by 10,000, now I can take 22 and it'll work harder to try and drive it to 0. It's not as sophisticated as MATLAB to do root finding. And then you can do the solver again and the same function. Well, no, it's staying there, stuck somewhere. So, but the valves are pretty open. It did drive that sum of squares down to 0, didn't it? So that's pretty good. So around 90 horsepower is what's used for the 2-pump option. Yeah. So that's actually a good solution for those pipe diameters. Now let's go back and say, I'm only going to have 1 pump, and I'm going to change those other valve settings. So put pump 1, 2, put it to 0. No head gain. It's like it doesn't exist. I probably want to boost this one up to about 80, so it's close, his initial guess. And I'm going to still change those valve settings, and I'm still going to try and drive the head balance equal to 0. So let's do data, solver. This time I've got to take out that one right there. So it only does pump 1 and those 4 valves. And it's still trying to optimize this cell right here. All right. Let's go ahead and solve and hit OK. And there you go. So it's about 77.4 or 8 with a pump of 139.2 horsepower. So the savings is the original 139 minus 89. It's about 50 horsepower less. And you notice that these Ks on the balance valves had to really be closed. They had to really close them to get the flow to force it through the 4th floor. Okay, you can look at powers in different parts where the power go. Let me see if I could show the power here. In valves, that's about the 50 that was lost. I know that if this one valve is open on the floor, it's about 1 horsepower continuously lost in that one valve. So it's about 50 horsepower that's lost above the partially closed valves. 58 just to push it through the air handling units. 31 of it are the 2 air handling units on that 4th floor that had the higher flow rate. A lot of power to push them through there. The chiller, about 21 horsepower to just push it through the chiller. And the friction in all the legs of the pipe is only around 8. So increasing the pipe diameter isn't going to help you. It's really the pressure drop or the pumping power required to push it through the air handling units, especially the 2 on the 4th floor.
Air handling unit?
Yeah.
You use the 1.2 Q.
Air handling unit, that's where we want to look at it, right? So we have 2 times this, which is, what is that? That's the air 1.2 times G11 squared. Let's go to G11. G11. There, it's Q. I'm using Q. All right. Why do I have a 2 there? Yeah, it's only 2 in the one leg. Oh, I copied the formula for the valves. Oh boy, this is always embarrassing, huh? So we drop that, fix this. Let me take a look here. That is the 2, and fix that. And let me double check this one. Oh, it had the higher flow rate, plus there were 2 of them. That's why it's so much higher. Well, you have to go back and rebalance it. So, sorry about that. Hit solver, and it looks like it drove it to 0, which is good. 78.8 horsepower. Why is it exactly the same? I guess it didn't change it much. Went through the air handling units. Did you get some numbers similar to this?
Yes.
And then if you do the sum of the horsepower, 139.2. All right. You got 134 something?
138.
That's pretty good. That's real good. Let's solve this problem. This problem is a lot like the homework problem due next time. So a line is used to transport 60 degree F water at 1500 GPM as shown. So they want to move 1500 gallons per minute. The current system consists of 1,200 foot of pipe, or 12,000 foot of pipe. The pipe is 8 inches diameter, Schedule 40 commercial steel with only one pump in it. The capacity needs to be expanded to 2,400 GPM. So that's an increase of 900 GPM, right? So you're going from 1,500, let me show you this, to 2,400. Did I do the math right? Is that a boost of 900 GPM? So you have 3 options. Option 1, just install a larger pump and use the existing line. That's option 1. Option 2, leave the existing pump and line there and install a new parallel pump and line, brand new pump with a brand new line, but the line will be a brand new 6-inch plastic pipe. So it's like another pump, another line, and there you go. That's option 2. So the current system will be running as well as the new system if option 2 is employed. And option 3 is replace with a brand new line, rip out the pump and rip out the old line and put in a brand new pump with a 10-inch, larger diameter, plastic pipe. So for those, compute the head gains and the power input for each of those options. It's like, wow. You need to compute a lot of things and then compare those. And include a 60% pump efficiency and electricity costs 8 cents per kilowatt hour. Estimate the annual electrical bill or cost for running each of those 3 options for 3,500 hours per year. So consider that being run full-time during a year. All right. Well, how do we solve this problem? We go back and we have no loops here. It's just a system like this. And you use Bernoulli's, and wouldn't you end it right there? And how would you want to write it? Energy per unit volume, energy per unit mass, energy per unit weight. Energy per unit mass is the preferred that the textbook likes, right? So it's pressure divided by rho plus 1/2 V squared plus GZ, all of that at the initial state 1. Any head gains equal to P over rho plus 1/2 V squared plus GZ at state 2, there's state 2, plus any head losses. Did I write it correct? All right. Let's get rid of the terms which are 0. What about the pressure at 1 compared to the pressure at 2? They're both atmospheric pressure. Boom. How about the velocity at 1 and the velocity at 2? Let's get rid of those because it's large tanks that you're moving. How about the elevation 1? Well, the elevation 1 is 200 feet. Elevation 2 is, what is that? 600 feet. So there's a difference. So basically what you're going to find is the head gain that the pump has to put in is going to be G times the higher elevation at the exiting tank minus the initial. So it has to boost it up, lift it, put it to a higher elevation, and has to overcome all of those losses. And so don't forget this term. I would say this is a elevation head gain that the pump has to put in. Okay, you can name that something if you like. Well, what about all these head losses? Well, we have the 12,000 foot of line. Isn't that going to be F L over D times the velocity head, or head velocity, head, the velocity head. Okay. Also, they have showing an inlet. Will there be a loss associated with the inlet? Yeah, and it's protruding in, and we'll just assume it's sharp-edged. And do you remember loss coefficient K for that guy? Yeah, 0.07, 0.08. Let's do this. In Chapter 1, they basically have reprinted a few of the pages of the Crane manual for loss coefficients. And I have that book. I should have brought it. It's on my shelf, an old copy. One of the students who graduated, I don't know, a year and a half, 2 years ago, he's working in Houston doing work. He sent me an email this week or last week and said something about he's doing piping calculations and designing for moving product in this Houston area and South Texas area. And he uses the Crane's manual. That's his go-to standard for calculating head losses. So if you look at this on page 18 of the textbook, for a pipe entrance sharp edge, they have a K of 0.78. So I know that in our table here, I think we have some other Ks, or you could look in your other fluids textbook. There is some variation, 20% at least, in some of these loss coefficients. But when in doubt, just go to a standard like that. Let's do this. Is there a loss for this exit? It's a submerged exit. It's not a free exit. You're not ending the point at that exit on your Bernoulli. The Bernoulli goes through that exit. It's a submerged exit. Is there a loss with it? And what's the K value? 1. Yeah. It's a tricky one. If they would have taken that pipe and put it up here and then just sprayed it out, you would have ended the Bernoulli right here. It would have been a higher elevation, and you would have no loss coefficient, but the exiting kinetic energy would not be negligible. Basically, you still have effectively a loss of 1 because that term has a coefficient 1 in front of it, 1/2 b squared. So the head losses for the minor are the K for the entrance, the K for the exit, and some others, but they're going to multiply by the velocity head. They multiply by the 1/2 v squared. All right, so those, the entrance and the exit with this K on the exit of 1, they say right here there's 20 standard elbows. What? They just tell you that this is going to have a few kinks, and so there's 20 elbows. So you're going to have 20 K of the elbows. How do you get the K of the elbow? A very easy one is table 1:1, and that K of a 90-degree standard elbow is given to be 0.75. If you're staying with the Cranes, it's a little more complicated, but they have it. It's basically for the Crane, the standard elbow, they say the K is 30 F of T. I understand 30. What's F of T? The friction factor, fully turbulent for that diameter pipe. And that friction factor, fully turbulent for that diameter pipe, there's a neat little table, figure 1-7, which gives it. And if you're running an 8-inch pipe, it's 0.014. So you're going to be different using that technique versus just grabbing the loss coefficient of, what did I say it was, 0.75. Anyway, this friction for 8-inch pipe, 0.014. All right, and you have 20 of those. Okay, what about a check valve? Same thing. You're going to look for finding what it is. Now that check valve, they have different types of check valves. I forget which check valve I grabbed. It's a swing. About 100. I think I grabbed 100 times F of T. And ball valve, if it's fully open, it's a very small loss, and it was 3 F of T. So for the ball valve, 3 F of T. But hey, you have them in there if they're fully open. You ever gone and looked at a ball valve when it's fully open? It's just nice. But then you close it, it stops the flow. K goes to infinity. Did I lose anything or miss anything? So we have a few of these things. We have 4 Ks of the check valves and 2 Ks of the ball valves. All of them multiply by the same velocity head, don't they? And that's our total head loss. You have the major head plus all of these. I should have put the plus sign there here. The minor losses. Okay. Let me just jump into Excel because Excel's good at that bookkeeping, isn't it? And this is the, which problem? 122? 27, right? All right. So I just inputted the information about water at that temperature. Was it 10,000 foot for the problem? What's in their text? Might as well change it to the numbers that are the problem. 10,000 for the problem book. Let's run with the problem in the book because I was going to change it up and be cute, not show you the solution, make you work. But here, 10,000, right? What about the elevation change for the book? It goes from 300 to 400, 100 foot elevation change. Right away, you can calculate that head elevation needs to be that many foot squared per second squared. If you divide it by G, you get it, guess what? The head elevation in energy per unit mass is numerically the same as energy per unit weight. It's 100. 100 foot-pound force per pound mass. All right, there's our steel. If you go with the other options with plastic pipe, the roughness of the plastic pipe is very low. See how much different it is? Drawn tubing and plastic pipes have very low roughness. Those are those F of T's I mentioned. The number of elbows, the number of check valves, the number of ball valves, K of the elbows, and K of the check valves. So I put all the numbers, and then I put the K values for those. And the inlet had a 0.78, and exit, submerged exit's a K loss of 1. All right. First of all, let's analyze the base case before we move to options. So the base case, you have 1,500 GPM running through it. That's the flow rate in feet per second. That's the mass flow rate. 8-inch diameter. They tell you, this is what I did because they told me the actual ID of a plastic pipe. I went and looked up the actual ID of the standard 8-inch Schedule 40 pipe. If you just said 8 divided by 12, it'll be very close, won't it? Let me put that where I can see some more digits in it. 0.66666, but this is 0.6651. So I guess if you're really struggling for 3 and more significant digits, then use that K, that diameter, inside diameter. Area velocity. Make a comment about that velocity for me real fast. What do you think about this velocity? It's moving pretty good, right? We don't want to boost it to 20 and 30 foot per second. It's not good for the pipe. So anyway, that's a pretty moving velocity. You're going to have a high velocity head with that velocity. Reynolds number is pretty good. You get a friction factor using the Churchill equation. And then you can just calculate all these head losses, right? So the head loss in the length of the pipe, it's 338. The elbows, 10. The check valve, 8. The ball valve, very little, 0.12. The inlet, 1.12. The exit, 1.44. You add them up. No, the elevation was 100. You add them up to 460. And right over here, what do I show? Where's the head loss due to? What's it due to? The majority of the head loss is due to pushing it through the length of the pipe. 74%. All right. So if you know that, then the pump has to accommodate that. It has to overcome the elevation head and all those losses. So the pump has to put in 460. You multiply by the mass flow rate, you get the work or the power of the pump. You divide by 550 to get the horsepower. Get it into units so you can see it. That's a big pump, 174 horsepower, but that's fluid power. If your pump's only 60% efficient, you have to pump in 290 horsepower of electric power to the motor pump combination to get 60% of that into the fluid. And if you're operating that many hours per year, 1 horsepower is that many kilowatts. You can calculate how many kilowatt hours of energy are needed per year. Get rid of that extra digit. It's not. What's that? 758,228. You will make some electric provider a lot of money, because at 8 cents a kilowatt hour, you're going to pay them $60,000, $61,000 a year just to run it, right? All right. Now, that's the base case. You're ready to go to the larger pump. So you want to get this flow rate through the system, true? If you want that flow rate through the system, the CFS goes up, the mass flow rate goes up. You didn't change the diameter. Look at the speed now of the flow. Compare it to what it was. The velocity head is now a lot higher. See that? So now all of those loss coefficients are going to be more significant. So let's get back over here. So for the larger pump, 84% of your head loss that the pump puts in is now due to the straight run. It's up from 74. And only 10% is really going into increasing the elevation. And your electric bill just jumped to $210,000 a year. So from 60, why so much? Because it's proportional to the velocity squared, and the velocity went up quite a bit. So really should think about putting in more square area of pipe. How do you do it? Additional pipe, that's option 3, right? So if we put in option 3, so we add the 6-inch, what you have to do is you have to say, this new 6-inch plastic pipe only takes, we're going to still run the existing pipe the way it's been running. It only needs to take in 900 GPM. And then you calculate the area, the velocity head, the Reynolds number, friction factor, and what you find is that it's still a lot of it's overcoming even friction in the straight run of the plastic pipe. Some of it's adding it, but you come up here, and just to run the plastic pipe is $43,000 a year. You add that to the 60 to run the previous, and now you're paying $104,000 a year. All right, sorry about this. I can see you're being tried. Oh, you can bring your laptop if you like to class and keep it open and try things. We're going to be using Excel. Sorry if I didn't mention that earlier. 2,400 GPM in a 10-inch brand new plastic pipe. You just do the same calculations. Let me not bore you, but what it does show though is this gives you the lowest percent due to just pushing it through the straight run of pipe of all these options, where most of the energy is going into lifting it, and you compare, and it's the lowest cost, $78,000 per year. So you could go with an option of almost 210, 104, or $78,000 a year. What do you think? Go with the minimum, right? Well, with that, I'll stop and see if there's any questions. Yes, sir. Thank you for your attention. We'll see you.